Brine solution flows at a constant rate of 4 liters per minute in a tank that initially held 100 liters of pure water. The solution in the tank is kept well stirred and flows out at rate of 3 liters per minute. If the concentration of salt in the brine entering the tank is 0.5 kilogram per liter, find the mass of salt in the tank after T minutes. When will the concentration of salt in the tank be 0.2 kilogram per liter? So one difference which we have in this problem as compared to the previous one is that we initially have pure water here. In the previous problem, we initially had a brine solution which had 0.2 kilogram of salt. And then the second difference is that the rate of outflow is different from the rate of inflow. So 4 and 3. In the previous problem, the inflow rate was equal to the outflow rate. Okay, but otherwise, there are a lot of similarities. So again, the first part is to find the mass of salt. So let X be the mass of the salt in kilogram in tank after T minutes. And we write X of T to indicate that the amount of salt is a function of time. You know, in calculation, we will omit the T. So the rate of salt entering the tank, we want that in kilograms per minute. So right now we have 4 liters per minute entering, and it's entering at 0.5 kilogram per liter. So when you multiply the 4 liter per minute and the 0.5 kilogram per liter, the liters cancel out, and the 4 times 0.5 is 2. So it means that the rate of entering is 2 kilogram per minute. And leaving the tank, so it leaves at 3 liters per minute, and then at any time the concentration is X. And now here there will be a difference. In the previous problem, since it was always 100 liters in the tank, it was 100 liters in the beginning, and then the inward and outward flow were at the same rates. So at any time it was always 100 liters. So at this point, we just had X over 100 in the previous problem, because X was the amount of salt and 100 liters is the amount of solution. So in this case, since the inward and outflow rate are different, so if we start with 100 liters, we won't always have 100 liters. So let's see what's going on. Since it comes in at 4 liters every minute and we lose 3 liters every minute, so it means that we are net gaining 1 liter every minute. So you see 4 liters entering and 3 liters leaving means that 1 liter gain happens every minute. So if 1 liter is gained in 1 minute, then in T minutes, T liters are gained. So it means that at time T, the concentration will be the volume of the solution will be 100 plus T, because we started with 100 and we just figured out that we are gaining T liters in T minutes. So after T minutes, it will become 100 plus T. So the kilogram per liter will be X kilogram over 100 plus T liters. So the liters will cancel out, and you'll have 3x over 100 plus T kilogram per minute. That will be the rate of salt leaving. And so the net rate of salt flow will be inflow rate minus outflow rate. Inflow, so let's first write it like this. Inflow is 2, outflow is 3x over 100 plus T. So the net rate, which we call as dx over dt, will be 2 minus 3x over 100 plus T. And in this case, x of 0, the amount of salt at time 0 is 0, because initially we just had pure water. So once again, this is a linear equation, which we can see if we bring this thing, this 3x over 100 plus T on the left side. So let me now undo to do that. Okay, so I brought the 3x over 100 plus T on the left. Or maybe we can just leave that step and copy it in the next line. Where we bring this thing on the left and the 2 stays on the right. So now this is linear because this is like dy over dx plus y times a function of x equals another function of x. In this case, x is playing the role of y and t is playing the role of x. So the integrating factor would be e power the integral of whatever comes with the x. So that's 3 over 100 plus t. So the integral of that is 3 ln 100 plus t. And then when you raise 3 to the power, the e and the ln will cancel out and it will be 100 plus t cubed. So that's the integrating factor. And then we know the solution is x is equal to 1 over I. So 1 over 100 plus t cubed times the integral of, you repeat the I, which is 100 plus t cubes times the right-hand side, which is 2. And the integral of that part is 200 plus t to the 4 over 4. And when you distribute this outside 1 over 100 plus t cube, it multiplies with this, leaving 100 plus t to the single power. And then the 2 over 4 is 2 in the denominator. And then c times this 1 over 100 plus t cube. And then we use the initial condition that x of 0 is 0. It means when t is 0, x is 0. So you substitute 0 for the x and the t. And this is 50. Bring it to the left with negative 50 equals c over 100 cube. And then the 100 cube multiplies here to give us negative 50 million. So c is negative 50 million. You substitute that in the equation, in the solution. So c is negative 50 million over here. So you end up with 100 plus t by 2 minus 50 million over 100 plus t cubed. So that's the answer for part A, where we had to find the amount of salt at time t. So let me show you. Right, that was part A. 100 plus t over 2 minus 50 million over 100 plus t cube. And then part B is when will the concentration be 0.2 kilogram per liter? And this I have not worked out yet. So let's do it together. When will the concentration? So the concentration, you know, is x over the volume. X is the amount of salt divided by the volume, which is 100 plus T, as we figured out here. So this part, the X over 100 plus T, that's the concentration. And we want to see when is that equal to 0.2, but we already have the X. So let's write, we want this to be 0.2, but we already have figured out what X is. So I'm just going to copy this again and substitute the value of x, which we found in part A. Okay, it's not letting me do it. So just think about it. So x over 100 plus t, it means both of these will be divided by 100 plus t. So when you divide 100 plus t over 2 by 100 plus t, you just get 1 over 2. So x over 100 plus t, so this part will be just 1 over 2. And then when I divide this part by 100 plus t, then I gain one more power in the denominator. So it would be minus 50 million over 100 plus t to the 4. And That is our x over t, so that needs to be equal to 0.2. And then let's make sure if it's yes, it is 0.2. So solving this for t, so we can first move this thing to the right side and bring the 0.2 on the left. So I'm going to cut this from here and take it to the right hand side and bring the 0.2 to the left. Right. So, oh, okay, I should not have done it on that one. So let me do it in the next line. First, we just copy this. Or let me just do. So I've just copied it. So actually I want to bring the 0.2 on the left. So we cut this one. Move this to the right. And bring the 0.2 to the left. Okay, 1 over 2 minus 0.2 will be 0.3. So I'll just rewrite this. This left-hand side is just 0.3. And then I can move this 100 plus t to the 4 on the left side and take down the 0.3. So that will give me this quantity equals 50 million over 0.3. Fifty, 1, 2, 3, 4, 5, 6 over 0.3. Okay, so we can calculate the 50 million over 0.3 and then take the fourth root. So I've divided it by 0.3 and then I'll take the fourth root. I get 113.62. So that's 100 plus t. So 100 plus t is equal to 113.62. That gives me t equals 13.62 when I subtract the 100. So t equals 13.62.